In this lecture, we'll see the Fourier transform of periodic signals. That is, we have already seen this DTFT is mainly applicable for non-periodic signals. Also, we can find the DTFT of periodic signals. Okay, so we can form the DTFT of periodic signal directly from its Fourier series representation, and the resulting transform, it consists of a train of impulses in the frequency domain with the area of the impulses proportional to the Fourier series coefficients. Okay, consider the periodic signal x of n with period capital N and fundamental frequency omega 0 equal to 2 pi by capital N. The signal x of n has the DTFS representation x of n equal to summation k over capital N xk e raised to jk omega 0 n, where xk is the DTFS coefficient. Now, taking Fourier transform on both sides of this equation gives Fourier of x of n equal to Fourier of the term in the right. Okay. Now, the Fourier transform of x of n is capital X of e raised to j omega, and this Fourier transform can be taken inside the summation. So, this is summation k over capital N xk into Fourier transform of e raised to j k omega 0 n. Okay, and we know the Fourier transform of e raised to j k omega 0 n is 2 pi into delta of omega minus k omega 0. This we have already derived, and the explanation we have seen in a previous lecture over the interval 0 less than or equal to omega less than 2 pi. Okay. Now, therefore, x of e raised to j omega equal to summation k over n xk 2 pi into delta of omega minus k omega 0 in the range 0 less than or equal to omega less than 2 pi, and x of e raised to j omega equal to 2 pi into summation k over n xk into delta of omega minus k omega 0, that is in the range 0 to 2 pi. Okay, since the DTFT is periodic with period 2 pi, it follows that x of e raised to j omega consists a set of n impulses of strength 2 pi into xk, where k equal to 0, 1, 2, etc. n minus 1 repeated at intervals of n omega 0 equal to 2 pi. Okay, so therefore x of e raised to j omega can be written as 2 pi into summation k equal to minus infinity to infinity xk delta of omega minus k omega 0. Thus, the Fourier transform of a periodic signal is simply an impulse train with impulses located at omega equal to k omega 0, and the strength of the impulse is 2 pi into xk. Okay, and all the impulses are separated from each other by omega 0. Now we will consider few questions. Find and sketch the Fourier transform of the discrete time impulse train x of n equal to summation m equal to minus infinity to infinity delta of n minus m into capital N. Okay, so it is very clear. See that it is an impulse train, and the impulses are located at multiples of capital N, integer multiples. That is, when m0, it is an impulse located at n equal to 0. When m1, it is an impulse located at capital N. See, delta of n minus capital N. So the impulse is located at capital N. When m is equal to 2, the impulse is located at 2n, and so on. This goes up to infinity. Similarly, for negative values of m, when m is minus 1, the impulse is located at minus n. When m minus 2, it is located at minus 2n, and so on. Okay. Now, the signal is periodic with the period capital N and frequency omega 0 equal to 2 pi by capital N. So, the given signal is for one period may be written as x of n equal to 1 at n equal to 0, and it is 0 for in the range 1 less than or equal to n less than or equal to n minus 1, and that is delta of n. Okay, so first we have to find the Fourier series coefficient, DTFS coefficient xk, and it is 1 by n summation n equal to 0 to n minus 1 x of n e raised to minus j k omega 0 n. Okay, and that is 1 by n summation summation n equal to 0 to n minus 1 delta n e raised to minus jk 2 pi by capital N into n, and it is 1. We know delta of n is existing only at n equal to 0, so it is 1 by n e raised to minus jk 2 pi by capital N into n at n equal to 0, and it is 1 by n. Okay. So we have evaluated the DTFS coefficient xk, which is 1 by n. Now the DTFT of a periodic signal is given by x of e raised to j omega equal to 2 pi into summation k equal to minus infinity to infinity xk into delta of omega minus k omega 0, and substituting xk equal to 1 by capital N into the above equation, we get x of e raised to j omega equal to 2 pi into summation k equal to minus infinity to infinity 1 by n into delta of omega minus k omega 0. So it is 2 pi by capital N into summation k equal to minus infinity to infinity delta of omega minus k into omega 0 is 2 pi by capital N. Okay. So we have an periodic impulse train and whose strength is 2 pi by n, and they are separated by 2 pi by n. See, multiples of omega 0. Okay, so that is represented here. Discrete DTFT of a discrete time impulse train, that is also an impulse train. Next question, find the Fourier transform of the periodic signal x of n is equal to cos omega 0 n with omega 0 is equal to 2 pi by 5. Okay, so here x of n is cos omega 0 n, and we know cos theta can be expressed in e raised to j theta form as 1 by 2 e raised to j theta plus e raised to minus j theta. Okay, so the 1 by 2 is see, it is written as two different terms, and we know the Fourier transform of e raised to j omega 0 n is summation m equal to minus infinity to infinity 2 pi into delta of omega minus omega 0 minus 2 pi m. Therefore x of e raised to j omega, that is Fourier transform of cos omega 0 n, is 1 by 2 Fourier of e raised to j omega 0 n plus 1 by 2 Fourier of e raised to minus j omega 0 n, and in the place of this Fourier transform, see, we are substituting this Fourier of e raised to j omega 0 n and Fourier of e raised to minus j omega 0 n. The difference is with the term omega 0, the sign of omega 0. Okay, so omega 0 is given in the question as 2 pi by 5, so that is substituted, and we have the expression or the DTFT of cos omega 0 n. And again, see, it is very clear, it consists of a train of impulses. The first term, the impulses are located at 2 pi by 5 plus 2 pi. The next term for m2, it is located at 2 pi by 5 plus 4 pi and so on. Okay, then when we consider this second term, the impulse located at, when omega 0, it is located at 2 pi by 5, omega 0, it is located at minus 2 pi by 2 pi minus 2 pi by 5, 2 pi minus 2 pi by 5. Then no, when m0, we have an impulse which is located at minus 2 pi by 5, that is minus omega 0. When m1, the impulse is located at 2 pi minus 2 pi by 5, that is 2 pi minus omega 0 and so on. Okay, so by substituting different m value, you can draw this spectrum x of e raised to j omega. Okay, next is find the Fourier transform of the periodic signal x of n is equal to sine omega 0 n with omega 0 is equal to 2 pi by 5. This question is similar to the previous question, and again, first express sine in e raised to j theta form. We know sine theta is e raised to j theta minus e raised to minus j theta by 2j. Again, the Fourier transform of e raised to j omega 0 n is summation m equal to minus infinity to infinity 2 pi into delta of omega minus omega 0 minus 2 pi m, and the Fourier transform x of e raised to j omega is 1 by 2j Fourier of e raised to j omega 0 n minus 1 by 2j Fourier of e raised to minus j omega 0 n. So x of e raised to j omega is 1 by 2j. Here they have substituted Fourier of e raised to j omega 0, and this is Fourier of e raised to minus j omega 0 n, and omega 0 is 2 pi by 5. Again we can draw the spectrum by substituting different m value, and see, they have drawn the spectrum. Here the difference is, if you consider, sorry, see the second term, it is minus 1 by 2j. Therefore the coefficient value, it is going to be minus j. Here there is a minus sign missing, so this 2 and 2 cancels, minus pi by j. Okay, so certain coefficients are having their value minus pi by j, and that is corresponding to the second term, and corresponding to the first term the coefficients are having a strength pi by j. Okay, thank you.